Swayam Prabha. Digital India. Educated India.
Here we are going to start how we can design the control system in frequency domain. Here first we would like to find the relation between the time domain specification, what we have done already, and the frequency domain specification. For the given time domain specification, we can come up with the frequency domain specification, which are basically the gain margin and phase margin of the system. Then we'll study how we can mitigate the slow varying disturbance signal and fast varying measurement noise in the system using the controller in frequency domain. What should be the controller structure or the control algorithm should be there to mitigate the disturbance and noise in the closed loop control system. We will discuss. Then we'll study how we can find the phase margin and gain margin from the given frequency response. Basically, in the frequency response, we'll plot the gain of the system with respect to frequency and phase of the system with respect to frequency. For the given gain cost over frequency and phase cost over frequency, you can come up with the gain margin and phase margin of the system. Then we'll study how we can design the PID control in frequency domain for the aircraft attitude control problem. Then we'll conclude this part. So in the next few lectures, we'll be involving to discuss this part and how we can design the controller in frequency domain. Then we'll wind up this part. In this lecture, we'll be discussing the control system design in frequency domain. If you notice in the previous lectures, we have discussed the control system design of a system where the system model is known. But in frequency domain analysis, it is not necessary. The system analytical model of the system needs to be known. And also, the control system we have designed so far, it is difficult to comment on the robustness of the system in the presence of uncertainty and measurement noise. But this problem can be dealt with frequency domain analysis. So let me go through some advantages of the frequency domain and domain analysis control system design. So let me write the advantages. The control system design based on frequency domain analysis is robust to the modeling uncertainty and attenuation of measurement noise. So the control system based on the frequency domain analysis can deal with this problem, the modeling uncertainty and measurement noise. Second advantage, the closed loop system stability can be analyzed based on the open loop frequency response. Third point is, unlike root locus method, the analytical model of the plant is not necessary for control synthesis. If you notice in the previous lectures, to design the PID control, the analytical model of the plant needs to be known. But in the frequency domain, it is not necessary. Based on the experimental data or frequency response of the system, we can come up with the control system design. So we can write based on the experimental system stability can be analyzed. And also, why this is important, because most of the cases, the suppliers may not provide the detailed analytical model of the system. They only provide the data, and from the given data, we can come up with the control system analysis. So for aircraft attitude contour, suppliers may not provide a detailed model, analytical model of the different subsystem for designing the control system. So this kind of problem can be dealt in the frequency domain analysis. Even the analytical model not available to us, we can come up with the control system stability. So these are the few advantages in frequency domain analysis. Now let's go back to our aircraft PD control system. Aircraft PD controlled attitude problem. And here we'll come up with some relation, how we can come up some quality conditions based on the frequency domain measurements as well as time domain analysis. And based on these relations, we can come up with the control system design. So first, let's go with the control system, PD control system for the aircraft attitude control problem. So there are two different models we have discussed, if you remember. One was the modified implementation of PD controlled aircraft attitude problem. So the block diagram we had, in the forward path we had KP, and here we have another summing point, and this is our plant, which is 1 upon IS square, and in the feedback we had KD is, this is our output, which was generated by YS. This is the feedback, and we have summing point, which basically connect the negative feedback, and this is our reference signal R of phase to be tracked, and this is the negative feedback. And this is actually modified implementation of the PD control system of the aircraft attitude problem. And we have standard implementation as well. If you look the PD control system, the standard implementation of aircraft attitude control problem. So their block diagram was, this is our PD controller, KP plus KDS. This is basically GC of S, control transfer function. And we have plant, which is 1 upon I squared, and this is our output Y of S. And this is summing point which connects the closed loop path. This is R of S to be tracked, and this is our negative feedback, which is negative. This is the modified implementation of the aircraft attitude control. We'll take this block diagram for come up with the relation between the frequency domain analysis and time domain analysis. So based on the time domain parameters, we can come up with the conclusion on frequency domain part. And if you are having frequency domain specification, we can come up with the time domain specification. This is very important relation that we are going to have now. Let me define this figure number 1. This is figure number 2. And from figure number 1, from figure, we are going to use figure number 2. Figure number 2, the open loop transfer function, we can write G naught of S equal to GC of S, GP of S, H of S. So this is our plant GP of S, and we have feedback H of S equal to 1. This is basically unity feedback. H of S equal to 1. So we can write GC of S AP plus KDS, and GP is basically 1 upon I square. This is 1, or we can write AP plus KDS divided by I S square. Let me define this equation number 1. As you have done before in the time domain analysis, as we have done in time domain analysis, we had two important relations between the damping ratio and natural frequency and the controller gains. If you remember, omega n squared equal to AP by I and 2 zeta omega n equal to AD by I. So here omega n basically undamped natural frequency of the system, and zeta damping ratio, and these parameters Kp and Kd are the controller gains. This is I is basically inertia of the aircraft. Now, to substitute these relations, if you substitute these relations in equation number 1, the OLTF, open loop transfer function, yields to be G naught of S equal to 2 zeta omega ns plus omega n square divided by S square. Now, this is basically in time domain, we can say. Now, we'll come up with the frequency domain analysis. Now, we'd like to start how we can come up with the relation between the frequency domain specification and time domain specification. So, to carry out the formulation in frequency domain, we'll substitute in place of S, J omega, the open loop transfer function. This is equation number 2, let me write. the open loop transfer function in frequency domain, we can write G naught S equal to J omega. We can write 2 zeta omega n J omega plus omega n square divided by omega square minus, and if you do the further simplify this equation, it will be omega n by omega square minus j 2 zeta omega n by omega. Let's note the equation number 3. And now, if you come up with the magnitude of this open loop transfer function, you can write this basically gain of this transfer function. Open loop gain in frequency domain, we can write J omega equal to square of the real part, we can write so omega n by omega 4 plus 4 zeta square omega n by omega square. Let me denote this equation number 4. This is how it is coming if you have some function, for example, x equal to a plus ib. Magnitude of the x we can write root over a square plus b square. This is very fundamental thing. Now, if you want to come up with the phase angle of this equation number 3, the open loop phase, we can write G naught J omega. This is the angle of the transfer function. For the numerator part, we can write 2 zeta omega n J omega plus omega n square. And for the denominator part, we can write minus omega square. And from this, the total angle yields from the numerator part tan inverse 2 zeta omega divided by omega n minus 180 degree. This is the angle, the minus 180 degree coming from the denominator part, because there are two poles at origin, and for each pole, and since there is no real part, only imaginary part, if you suppose there is j omega square. So there are two poles at origin. For these two poles at origin, we can come up minus 90, and it is minus 180 degree. Let's note the equation number 5. So now, since the frequency omega is positive here, since the frequency omega is positive, the phase angle of G naught J omega lies, can write minus 180 degree to, can write G naught J omega, right, angle and minus 90 degree. So why it is happening? How it is happening? because when omega equal to 0, that time tan inverse 0 equal to 0 degree, and omega goes to infinity, then tan inverse infinity equal to 90 degree. So based on this condition, we are getting, if we apply omega equal to 0 and omega equal to infinity to equation number 5, we are getting this range. And let's denote this equation number 6. We'll come up with the another important point in frequency domain, gain cost over frequency and phase cost over frequency. Those are very important part to come up with the specification in frequency domain. But this is, I hope it is clear, this is the magnitude of the transfer function and the phase angle of the transfer function, which is denoted by equation 4 and 5. So now let's determine an expression for the phase margin. The definition of the phase margin I'll come very soon, how we can define for a system, but for the time being, how we can determine the phase margin for this open loop transfer function. Find to determine the phase margin, we need to calculate the gain cost over frequency For the time being, please bear with me. I'll explain all this, what is gain cost over frequency, how to define the phase margin. I'll explain very soon. So at the gain cost over frequency generally we find the phase margin, and gain cost over frequency actually, the gain cost over frequency let's denote omega z, at which the gain of OLTA, open loop transfer function, is unity. So it means our open loop transfer function we have denoted by G naught. The gain of open loop transfer function at the gain cost over frequency omega z equal to 1. This is actually what is telling. Let's denote this equation number 7. And using equation number 4, so total gain already you have found of a system. This is the gain of the system, equation number 4. And at gain cost over frequency, equation number 4 can be written as omega n by omega z. Instead of omega, we are writing omega z. This is the gain cost over frequency. So there are 4 plus 4 zeta squared omega n divided by omega z square whole root equal to 1. And after simplifying, this is omega n by omega z, we have 4 plus 4 zeta square omega n by omega z square equal to 1. So we have to solve this equation. Let's consider some parameter q, which is denoted by omega n by omega z square. And let's denote this equation number 8. Substituting q in equation 8, we form the quadratic equation, which is q square plus 4 zeta square q minus 1 equal to 0. And solving this equation, solving equation 9 yields q equal to minus 2 zeta square plus minus 4 zeta, 4 zeta to the power 4 minus 1. So this is the solution of equation 9. And since we are considering the positive real values of omega z, so only positive solution of equation 10 is valid. So using the definition, using the positive values of q, we find that there is only one gain possible frequency. What is that? So let me write. So we can write q equal to, we will not take the, so we'll take q equal to minus 2 zeta square plus root over 4 zeta to the 4 minus 1. We will not take the negative part. So since we are assuming the positive real value of omega z. So in that case, we can write q equal to omega n by omega z square equal to minus 2 zeta square plus 4 zeta to the 4. So it is actually, I have type for this. This should be plus 1. Should be plus 1. And also it should be plus. Yeah. And from this, since we are assuming the positive value of omega g, so omega g you can write omega n root over 4 zeta to the 4 plus 1 minus 2 zeta square root. So this is basically very important value which relates between the natural frequency and gain crossover frequency. Relates between omega z, omega n, and damping ratio of the system. So from this relation, we'll come up with the time domain specification relation, and we can connect them at frequency domain specification and time domain specification. Then how we can design the control system in the given time domain specification, how we can come up with the frequency domain control specification we'll discuss. Now, we would like to find the phase margin of the open loop transfer function. If you refer equation number 6, which is given by this expression, the phase margin from equation 6, it is clear that the phase margin is positive and given by phase margin equal to 180 degree plus total phase at gain cost per frequency. So let's denote this equation number 12. This is very important to find the phase margins of the system. This is the formula we use. Now substituting equation 11 and equation 5 into equation 12 yields, we can write phase margin equal to 180 degree plus Z naught J omega Z. So we'll find the phase of G naught at the gain cost over frequency by equation 5, by this expression, equation 5. And if you substitute that expression here, you will get 180 degree plus tan inverse 2 zeta omega Z omega n minus 180 degree. Now, if you substitute the value of omega Z, which you have in equation number 11, we substitute in this equation, we are having tan inverse. Okay, let me cancel this term. So tan inverse, let me write 2 zeta omega Z divided by omega n. Now, if you substitute the expression of omega Z in this expression, it yields to be 2 zeta over 4 zeta to the 4 plus 1 minus 2 zeta square to the upper half. So this is the expression we are getting. Now, if you notice this expression, equation number, let's denote this equation number 13. This equation number 13 basically relates. Equation number 13 relates between phase margin and damping ratio of the system. This is very important equation. So here actually for the given damping ratio, we can find the phase margin of the system. If we consider an underdamped system where the damping ratio varies between 0 to 1, the relation between damping ratio and phase margin can be plotted as for this damping ratio range, So we are having the response plot. This is the phase margin in degree, and this is the damping ratio. And let me consider this is 0.2, 0.4, 0.6, and 1. And if you break this y-axis like this, it's 10, 20, 30, 40, 50, 60, 70, 80, 90. So this is the phase margin where the values are in degrees. and we can come up with some relation. Should be something like this. So it means for the given damping ratio, we can find the phase margin. Suppose the damping ratio is given 0.4. So we can at 0.4, we can come up with the what should be the value of phase margin. We can get those values. So this is very important relation between the phase margin and damping ratio. So now we'll see how the damping ratio and maximum overshoot, also the phase margin and damping ratio. Again, if you notice, the damping ratio and maximum overshoot are related by, again, the damping ratio and maximum overshoot are related by MP, the maximum overshoot, equal to e to the power minus zeta 1 minus zeta square into 100%. And since in this figure 3, in the figure 3, basically it is related between the phase margin and damping ratio. And also we can come up with the relation between the phase margin and maximum overshoot. So here also the relation between MP and damping ratio is given by, you can come up with some relation. So this is y-axis, where we are plotting the maximum overshoot in percentage, and this is our phase margin in degree. And if you plot this is like this is 10 degree, 20, 30, 40, 50, 60, 70, 80, 20, 20, 30, 40, 50, 60, 70, 80. And if you looking at the y-axis by this 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And the relation between phase margin and damping ratio, the plots for this can be something like this. Relates between MP and phase margin. So if for example, in the problem, if the maximum overshoot is given to us, then we can, from this plot, we can come up with the phase margin of the system. So this is how we can relate between the time domain specification and frequency domain specification. Now we have another also relation where the rise time and settling time, how they are connected. Let's look with the gain cost over frequency. Suppose the phase margin has been specified or given to us, and also for the given phase margin we can find the damping ratio. Since phase margin is specified, and for the given phase margin from this plot, we can find the damping ratio. Damping ratio. The expression, now let's look how the gain cost over frequency and settling time are connected to each other, or rise time, how they are connected. So let's first start with the rise time. As we have done in time domain analysis, the expression for rise time, we can write TR equal to pi minus beta divided by omega n root over 1 minus zeta square. So where beta equal to tan inverse 1 minus zeta square by zeta. This is the beta. So now, if you use the equation 11 here, this equation, using equation 11, we can find the relation between the rise time and gain cost over frequency. The gain cost over frequency in place, basically we'll substitute the omega n here, because from equation 11 we can come up with the expression for omega n, and that expression we can substitute here, so we can find the relation between the TR and omega n. So we can write the gain cost over frequency, we can have omega z equal to pi minus beta divided by TR by 1 minus zeta square and 4 zeta squared plus 1 minus 2 zeta square. So this is how we can write. So this is basically relates between omega gain cost over frequency and rise time. Now we'll look the settling time constant. Also from the time domain analysis, the expression for settling time, we can write Ts equal to natural logarithm 0.02 1 minus zeta square divided by zeta omega n. Again, if you substitute the value of omega n from equation 11, if you substitute here, we can find the relation between the Ts, settling time, and gain cost over frequency. So with the relation of equation 11, we have the expression for omega z in terms of settling time. We can write natural logarithm 0.02 1 minus zeta square divided by zeta Ts 4 zeta to the 4 plus 1 minus 2 zeta square whole root. So this is how we can connect the time domain specification with our gain cost over frequency. This is how we can find also phase margin, gain cost over frequency, and if you have phase margin, we can come up with the frequency domain control system. So we'll come up with those things later. So the conclusion of this lecture is, we can write, we have seen that if the phase margin is given specifications of the closed loop control system. Control system, namely rise time, settling time, maybe on the given gain cost over frequency. This is a very, very important part, how we can connect the frequency domain analysis, what we are doing in open loop transfer function. And we are finding the system specification in time domain specification of the closed loop control system. Let's stop it here. We'll continue in the next lecture.